So I'm going to talk about automotive, and I wanted to make it interesting for the audience here. So I decided that I would go under the hood and give you some examples of how we get IP, intellectual property blocks, working in an automotive environment. So the presentation is very design-centric. I'll cover some key trends. I think it's interesting to appreciate what's going on in the market and what's driving the requirements for automotive compliance. And then I'll give you some introduction into the compliance requirements. We'll get into some details of what is needed to make automotive compliance. And then I'll give you a summary of some of the automotive IP that we're working on at my company, Synopsys. So almost 50 years ago, people started getting concerned about emissions in the environment produced by cars. So in countries where the governments actually cared about controlling emissions, there was a move to reduce the amount of emissions that cars were generating. And of course, the automotive companies recognized that and tried to build technologies around those emissions requirements. So especially in Germany, Japan, and in France, there were regulations to control the nitrogen oxide being emitted by cars into the atmosphere. And so this is an example of Volkswagen. They came up with a concept to control the emissions that went from looking at the coolant temperature all the way to the amount of oxygen that was generated in the exhaust. So they had sensors around the car, and they wanted to be able to take all that information, all that data, and control the engine's fuel injection. So this is how it was done. So they had dozens of sensors from the coolant all the way to the exhaust that were looking at the types of control and emissions that were happening in the car, and they used an ECU, so an electronic control unit, to control the spark timing. So I'm still referring to a traditional car with cylinders, right? So this is a four-stroke engine. It has something called spark plugs and spark timing, and the sensors were looking at the timing of the sparks in order to manage the emissions. This required a computer. We're talking about 1968, so 50 years ago. We're talking about a computer that needed to be able to do millions of calculations per second to optimize the fuel injection. And the way Volkswagen portrayed this in the market, in their adverts, was an electronic brain. Volkswagen's electronic brain, it's smarter than a carburetor, okay? It's kind of interesting because now you've heard presentations from our CEO, RTR at the keynote, and he was talking about deep learning and essentially electronic brains, but this is fast-forwarded 50 years, again, for automotive applications. This electronic brain that controlled the carburetor was manufactured by a company called Bosch, and essentially it was an electronic fuel injection system. So the motivation to get the computer in the car 50 years ago was to control emissions. So if we fast forward to today, I got this summary from BMW with their kind permission, and what they were saying, what they showed was that the amount of electronics in an automobile, in a car, is substantially increasing, and you can see that from the arrows pointing upwards. So if we go back to the ECU, the electronic control unit, there are a couple of very interesting statistics here. So the number of ECUs that's in a car today is about 200. So if you're looking at the top BMW, the top Mercedes, they probably have about 200 ECUs compared to that one ECU of the Volkswagen 50 years ago. There are also legacy ECUs employed in cars that do a lot of these support functions. And then other interesting statistics include the amount of cable that's used in a car. So 3.8 kilometers, that's almost 2 miles. So you've got almost 2 miles of actual cable running around a car doing a lot of the signal carrying of the ECUs. I'm going to look at the communication technologies that are in the car, and this is what forms the interface IP portfolio that we'll talk about in terms of automotive-grade performance. So looking at the megatrends in terms of what's impacting semiconductors for cars, this information I got from Infineon, what they said was that there are 4 trends impacting the semiconductor content that goes into a car. The semiconductor content that goes into a car is expected to be around $31 billion in terms of revenue. It's huge, okay? That's the same revenue as TSMC's entire business. So you can see why lots of companies are developing chips, lots of companies are developing IP to go into this market because it's a massive market and it's growing. So there are 4 megatrends: ADAS, or autonomous driving. And here the trade-off is really looking at how much automation the car supports. So from fully autonomous to semi-automated to a little bit of driver assist, which is what commonly is happening today. Then you have all the emission requirements that I mentioned at the beginning, which kicked off this industry 50 years ago. And these mandate the amount of emissions that go into the atmosphere. And this impacts the way the powertrain is developed. You also have advanced security. So it's seen today that all the electronics that go into cars, they pose a security threat. And there are lots of examples you've seen in the media that show fairly serious breaches that have impacted a car's performance through some kind of security breach. And I'll touch upon that later on in the presentation. And then finally, connectivity. Remember all those cables, almost 2 miles of cables that exist in a car today? That connectivity is becoming very advanced. It's very difficult today to tell which part of the car is actually the car and which part of it is the internet, right? Because all of these things are merging into one. The cars are communicating to other cars, so you have vehicle-to-vehicle communication. And you also have vehicle-to-X, or vehicle-to-infrastructure communication that goes up into the cloud, into all the big data analytics and deep learning. So 4 megatrends. I'm going to focus on the connectivity megatrend. And this I got from, with permission from BMW, from Dr. Kirsten Matthias. She allowed me to use this slide. She presented it in Munich at the beginning of this year. And here, you can see a lot of interfaces like HDMI, USB, LVDS, Ethernet, increasing in terms of their bitrate requirements over time. So it means that the connectivity requirements in a car are increasing in terms of their bandwidth needs, okay? What is causing that? That's kind of interesting. So what's causing that is that the display size and resolution, the increased application data rate, as well as the safety features of uncompressed real-time data are pushing for more high-speed links, okay? You've got big displays, you've got a lot of communication going on, you want uncompressed real-time data for all the ADAS-type applications, and that's requiring the need for faster Ethernet, for faster USB, for faster FlexRay, for faster CAN. Generally, what I would say is that the connectivity protocol that seems to be emerging as the standard moving forward is Ethernet. Okay? So we'll talk about Ethernet later on in the presentation, but Ethernet seems to be the standard that's taking over from CAN, it's taking over from LIN. And one of the reasons is that you can use some of the early packets in an Ethernet protocol for security to kill some of the side channel attacks that come into that protocol. Okay? So connectivity is a very important aspect of the automotive roadmap. At Synopsys, we track a lot of this type of information. We probably touch every single customer that's developing an automotive chip in the world. And this is actually tracked by Sushil's team that introduced me to this presentation. And Sushil's team tracks the automotive IP requirements in terms of their end applications. So this shows ADAS, infotainment, body electronics, the V2X, and some other stuff, okay? So clearly, you can see over the last year that we've been tracking this data, we have a lot of inquiries coming in that are interested in ADAS and infotainment, okay? So if I overlay that with a market view, so this survey came from a company called IHS, and what they're showing here is basically the same information, but from a much larger perspective. What they're showing is that all of these particular segments are increasing. The orange one, that represents ADAS, That's also growing, so it matches the data that we're seeing at Synopsys. So the ADAS requirements, according to this particular survey, has a growth rate of at least 10%, and it's going to be about a $3 billion market. So again, ADAS is a very significantly growing market that requires semiconductor content. We did another survey. Again, this is Synopsys data, okay, produced by Sushil's team. And this is very hard to get this information, so it's actually very exciting. What this shows is the process node these customers are using for automotive chipsets, okay? And here you see 7 nanometers. Can you imagine that? 7 nanometer chipsets in a car. That's amazing. 16, 14, okay? 14, 16, 7. These are all FinFET technologies. And then you see 28 and 40 nanometers. So basically, when we looked at this data, again, it was produced over a year, it showed that the demand for FinFET technologies, 16, 14, and 7, is outstripping the demand for some of the established nodes. And this, from a view of Synopsys, is driven by ADAS. So ADAS is driving the advanced technology nodes. A lot of this actually was boosted by companies like NVIDIA and Qualcomm that made announcements late last year and early this year. So NVIDIA announced a chip that was based on a 16 nanometer technology from their graphics heritage that drove ADAS applications. Qualcomm revealed a new generation of Snapdragon based on their 820A. And this was a deep learning chip developed on a 14 nanometer technology for automotive applications. I'll talk a little bit about some of the memory interfaces later on in the presentation, but just to give you some perspective, the current generation of DDR3 has about 2 gigabytes of memory density. This will give way to LPDDR4 with about 8 gigabytes of memory density. So high-end ADAS is driving the interest for 7 nanometer, 16 nanometer, 14 nanometer FinFET technologies. So I talked about LPDDR4. We're seeing interest in Ethernet, Ethernet AVB, audio-video bridging. I'll get into more details about what that means. MIPI is also used in displays, as well as HDMI, PCI Express, SATA, and analog IP, embedded vision, security, and then you see some of the other things like fusion, data fusion, sensor fusion. All of these things require a concept called functional safety, which we'll deal with in a few slides. Okay? Key points, ADAS is driving the advanced nodes. I gave you some key trends as to why we're here, why we're developing chips and IP at 7 nanometer, for example. Now I'm going to give you an introduction to automotive compliance. So about 3 years ago, my company decided to formally roll out roadmaps on automotive for both EDA and IP. And formally meaning that we were working for many years with customers in the automotive market, but we would work with those customers in a very closed environment through statements of work. And about 3 years ago, we decided that we're going to make a product strategy, especially on the IP side, to support automotive compliance. And we had to learn all these new terms, which I'm going to go through with you today. And about a year afterwards, we became very familiar with these terms, and we thought we were experts. So we were able to say, you know, ISO 262, TS 16494, ECQ 100. It just rolled off the tongue. And we thought we were experts. Now, having done this for 3 years and worked with some leading customers on 7 nanometers, I kind of realized that no one is really an expert in automotive compliance. Everyone is learning this together. And it's very interesting working with the foundries, working with the end customers, talking to the system OEMs and the IP developers and IP community to figure out what you need to do to meet automotive compliance. Right. So I'm going to walk through some very introductory material before we get under the hood, okay? So there are 3 key areas. So when you're first looking at automotive, the 3 key areas are functional safety, reliability, and quality, okay? Those are the 3 key areas to meet automotive compliance. So I'm going to go through each one of those in a little bit more detail. Functional safety. This is defined by a standard. It's called ISO 26262. And it defines the functional safety assessments to ensure a certain safety level. That safety level is defined by ASIL. Okay? The example I'm giving, so this is a picture of a white paper that was written by TI very recently. This example shows you all the ADAS requirements that's needed by the high-end cars. So here we're talking about functional safety for an ADAS chip. The safety levels are defined by ASIL. Now, it gets a little bit more complicated than that. There are 4 safety levels, ASIL A, B, C, and D. And typically, D is the most secure, most reliable, and A is the one that's very similar to a consumer application. So ASIL defines the safety level. Within functional safety, you have processes and standards, and these are set by FMEDA. So FMEDA is failure mode, effects, diagnostics, analysis. Don't worry, we'll get into more detail about these things in a minute. The goal here is to minimize any random hardware failures. Okay? There are standards governed by TÜV SGS that grant SoC companies, IC companies, compliance to functional safety. So FMEDA is one of the deliverables to meet ISO 262. It defines the functional requirements. It applies to the rigor in your development process. You need to take necessary design measures in order to meet that. And there are a lot of systematic analysis techniques applied to functional safety. Okay? That's the first thing you need to do in order to meet automotive compliance. The second thing you need to do is look at reliability. At a very simplistic level, for digital IP, so RTL blocks, you have to add extra functionality in order to meet some of the reliability requirements. For hard IP blocks, you need to do a lot of silicon characterization testing at elevated temperatures and environmental conditions. This is all defined by AEC Q100. This defines the reliability requirements. And I've given some examples here. You're looking at things like fault simulations, fault grading. You're looking at accelerated environmental testing and lifetime simulation tests. You have a specification on the temperature. So in automotive, we talk about grade 2, grade 1. These refer to the junction temperature of the device. Grade 1 is the most rigorous. It's at 150 degrees junction. You have reliability tests related to electromigration. Electromigration at 7 nanometers is a challenging topic because the metal lines at the lower levels, when you're looking at MX, for example, have very high impedance, are very thin, so they're very susceptible to electromigration failures. So what we've done in the development of some of these IP blocks is understand that the EM requirements need to be understood at the schematic design level. So we back annotate the schematics with all the EM effects so that when we're laying out the devices for our USB or PCI Express or LPDDR4, all those EM currents are actually part of the schematic simulation. There are electrical verification tests related to ESD and latch-up. So what's, again, very interesting is that in automotive, you see the push for advanced technology nodes. The latch-up and ESD requirements haven't changed, so there's no relaxation of ESD, for example. So we're seeing requirements for ESD going up to maybe 500 volts or 9 amps, depending on the way you look at it. And all of this is driven by very large packages. So the packages define the CDM, the charge device model of ESD, in order to hit 9 amps reliability. You have other tests that are at the SoC level, and as an IP company, we need to understand those. And these include things like wire bond shear test for packaging, as you can see from this graphic. Not all the tests apply to all IP. That's another interesting thing. So ESD, for example, is required for high-speed memory interfaces like LPDDR4, but it's not required for the memory compilers. It's not required for embedded memories. So AEC-Q 100 defines what's needed for reliability. So that was the second pillar. The third pillar is quality. So I've summarized here all the quality requirements. Basically, quality is all about ensuring very thorough documentation and processes, and people to audit and manage that flow. So you define, you implement, you analyze, you standardize your development flow. You have quality management deliverables. You have an infrastructure that does that in terms of compliance reports. You have dashboard technologies and reports. You have a repository to track all the IP releases, and you can offer internal and external audits per a standard called DFMEA. So DFMEA is Design Failure Mode Effect Analysis. So a lot of acronyms. And the quality standards are all governed by TS 16949. So we talked about these three areas: functional safety, reliability, and quality. Once you understand what it takes to meet those three requirements, you can claim to have some understanding of building automotive-grade SoCs or automotive-grade IP. So just to kind of summarize the three areas, so ISO 262, functional safety assessments, you have a concept called ASIL, which defines the integrity of the automotive safety level, A, B, C, D. For reliability, you have AEC-Q 100, and for quality, you have the standard called TS 16949. In addition, in order to really kind of support the compliance requirements, what we've done is we have an internal product management process, which applies to all of the IP development. We have 9 safety engineers. So these are people that don't actually do any IP development work. Their job is to ensure that we implement the policies, the processes, and the procedures. They are certified by a committee called the Semiconductor Automotive Functional Professional Organization, SC-AFSP, in order to be able to say that we support all these compliance requirements. So as well as meeting these 3 pillars, you have to have safety managers that basically police your development flow and are ready to support an audit for an automotive customer if needed. Okay? So now I'm going to get into under the hood. I'm going to get under the hood. So you have the basics, hopefully. So just keep in mind all the things I've been saying about functional safety. It applies to this part of the presentation now. So in order to meet functional safety, in order to meet this ISO 26262, you need to develop a new development flow. You have additional deliverables and features. So the additional deliverables, I'm giving an example of PCI Express. PCI Express is an I/O subsystem that's used in automotive applications. You have these deliverables. You have an FMEDA report. You have a certificate to say that you're meeting ASIL B or D. There are safety manuals associated with this, and you have a certification report. In addition, there are work products that are available to our customers in the automotive market, and you can see that list here. So safety plan, verification reports, configuration management plan. So a lot of documentation. The additional features, and I'm giving a PCI Express example again, and I'll get into more detail on the actual RTL changes that we make to a PCI Express controller in a few slides, but I just want to give you the introduction here. The additional features include things like RAS, reliability, accessibility, and serviceability. And those features need to support things like data protection, error injection. And if you meet all these requirements, and you're able to show traceability, meaning the person in marketing that actually got the customer requirement to the person in engineering that's delivering the package can be traced, that gives you the roadmap to support the ISO 262 requirements. And also, you can see that there's lots of work here. So there are trade-offs. And one of the interesting things is that We talk about safe IP in terms of it's met the functional requirements, and we talk about IP that's not safe. In some examples, you can combine safe IP in a protocol with IP that's not safe and make it safe. So the example here is like a PCI Express, for example, where you have a high-speed SerDes for the electrical interface. If you couple that with the functionally safe controller, that whole system becomes safe because all the CRC type checking for RAS can be done in the digital IP block, thereby not necessitating making the same changes to the hard IP. So there are trade-offs. You need to make sure that this is agreed upon with all the auditing and management of the systems, but you can make some trade-offs in the IP development in order to support the functional safety requirements. So it's onerous, but it's not so onerous. All right, continuing on with the theme of functional safety, I'm giving an example of, it's an Audi. It's my favorite car because I drive one. Here, actually, it's very similar because my Audi does communicate now through Wi-Fi to the cloud. I have all my music loaded on it, and it's quite fun. So this car gives the same example of communicating to public clouds, to different clouds that are controlled by the automotive manufacturers. And then you see all the more serious stuff related to ADAS, brake and powertrain control. So there's lots of hardware requirements to enhance the functional safety, in addition to all the things I mentioned earlier to meet functional safety. And you can see them here. In the digital IP blocks, you can add write protection to your elastic store. You can add parity to your parity protection to your data path, protection for your read-write memories. You can have dedicated interrupts, parity check on state registers, and you add redundancy for error handling and the elastic buffers. And I'll go into a bit more detail in terms of redundancy and how redundancy impacts your ASIL level. So the example I'm going to give later on is a microprocessor where we're meeting ASIL D, the highest requirements for functional safety, but we're adding so much redundancy in order to do that we've got to include safety monitors in order to meet that. One point here also is to understand the test benches. Remember, we're doing IP design, we're doing development, right? So you've got to build test benches once you build the IP, right? So for digital IP, you have controller test benches, right, for the RTL. Those test benches need to have some kind of identification. That identification includes things like error injection. You have different verification techniques. And these are verification techniques that almost get into the realm of formal verification. Things like assertions, properties, and then going into hardware and software validation. So you can even apply formal methods to go and enhance your functional safety requirements for digital IP. This example gives you the development for foundation IP. These are logic libraries for grade 1 requirements, okay? Grade 1 is 150 degrees junction temperature. So I've got a few rows here. I'm talking about setup, hold. So what we're doing is we're setting up a profile called a mission profile, okay, at 150 degrees C. And I get into more, I'm introducing a new concept called a mission profile. And I'll talk about the mission profile in more detail. But here, just kind of understand that for a logic library, you have a setup requirement and a hold requirement that needs to meet a certain junction temperature. And so you have a setup and hold at grade 1, 150 degrees C. And you have something called super overdrive. I love that term, super overdrive. Going to make your car go faster, right? Actually, I was at an automotive panel yesterday evening, speaking with the other panelists were from NXP and ST, so highly respected companies in the automotive world, and they were telling us that there's a real challenge in developing ADAS chips where you've got to do a lot of this number crunching for real-time data processing and having to drive the devices above their operating range in order to meet the speed of the processors to do all that number crunching. However, the reliability requirements of automotive basically tell you not to overdrive transistors, okay? So reliability requirements tell you not to overdrive, and I'm standing up here telling you, actually, we need to super overdrive in order to meet all those real-time processing requirements for your favorite microprocessor that you're using in an ADAS chip. So, extended sign-off corners for grade 1 requires a setup and hold at 150 degrees junction. It requires super overdrive, taking the voltage of the device 20% above its nominal. Then you need to do things like burn-in. And burn-in includes HTOL, and I'll talk about HTOL and burn-in again in more detail. But you need to meet the functionality of burn-in with the HTOL requirements. And then you have end-of-life SPI simulation models to support the mission profile. Okay? The aging really boils down to how you mitigate against NBTI, negative bias thermal instability, what you do with hot carrier injection, how you understand the requirements of the breakdown of the oxide, so the time-dependent oxide breakdown, and how you develop end-of-life SPICE models to manage all of the aging effects. And finally, when you're building logic libraries to support grade 1 operation, you have to analyze the SoC for asynchronous aging using special vectors. So things on your ADAS chip age at different rates. So my marketing team told me not to show this slide. This was too complicated, but I'm going to show this slide. And I'm not going to make a mess of it, OK? So, all right. When we first started in automotive sort of IP development, one of the questions internally was, are your layouts, what's the impact of your layouts? Are they going to get bigger because you've got to do all these reliability requirements? You've got to meet all these reliability requirements. So we didn't know the answer. Some people said, yeah, 30%. Some people said 20%. Some people said 5%. We just didn't know. So what I've done here is I went back to some work we did, and this is for a NVM technology. This is actually a slide I got from my colleague Martin Nizet, who's a really good person to talk to for this type of automotive qualification. So we took an NVM technology, and we looked at the impact of that NVM array in terms of failure probability at elevated temperatures, right? So the terminology here, so this is real. This is how we actually size devices for some of these things. So F represents the end-of-life failure rate. That's expressed in ppm. P represents probability that a single floating gate fails. Okay? N represents the number of bits per word. M represents the number of rows. And B represents the number of error correction codes per word, okay? So this is an area calculation for ppm. What we're targeting is 1 ppm to meet automotive compliance for this particular layout. So this is what we got, okay? So I've got a couple of things on this slide. I'm showing you the area trade-off, and then I'm showing you the actual area in terms of a GDS2 plot. So the goal here is to understand the process node, the target node, and how that impacts the bit cell architecture, okay, which you see on the right-hand side. So I've got 4 examples: a single-ended architecture, a single-ended architecture with ECC, a differential architecture, and a differential architecture with ECC. The color coding, so purple represents 180 nanometer BCD technology. 90 nanometer is represented in orange, and the green represents 40 nanometer. So I talked about 7 and 16 and 14. I also want to give you perspectives that not all automotive chips are in those leading edge nodes. Okay? So this is an example of something that's in a more established node. So the first thing to note, in order to meet that 1 ppm level, so if you look at that graph, that's the axis on the, that's the y-axis. In order to meet the 1 ppm level for automotive, the single-ended array completely fails. Okay? If you go across to the second set of bars, you see if you add ECC at 180 nanometer, you can now meet the automotive requirement. But if you go to a smaller node, like 90 or 40, you actually fail automotive requirements. Okay? Then if you get to a differential architecture, you can meet the automotive requirements in 180 and 90. And then if you add differential and ECC, all the technologies actually meet the requirements in terms of PPA in automotive. So this is very interesting because what it's telling you is that as you get smaller in your technology nodes, the chances of meeting automotive reliability are lower. So conceptually, you have to make your layouts bigger. Plus, you have to add design techniques like differential stages or ECC in order to meet that PPM requirement. And if you're interested, the layouts on the right-hand side, the top represents the single-ended, and the bottom represents the differential. So the key message is that at more advanced nodes, you need to compensate for the higher likelihood to compensate against floating gate failures by basically having a larger bit cell. So product reliability impacts the way you implement your design, okay? So I'm going to try and give you some perspective of what that means. So I introduced this concept without telling you what it is. I introduced this concept called mission profile. And hopefully, after walking through this, you'll understand this a little bit better. In the past, before we got serious into automotive, the reliability was related to the number of hours, power on hours, that your IP or your SoC was working at. So people talked about 8K power on hours, 22K power on hours. And just to kind of give you a perspective of what that really means, and this is some information I got from my colleague Ron, who's sitting over here, who's our automotive expert. He told me that 22 kilo power on hours is essentially a New York City cab driver driving a cab all day, or closer to home. It's one of those self-driving cars that basically spends the whole time driving. So what you're talking about is a very high on time, and a very high on time is going to impact the way you think about the reliability of your chip, clearly. So the red represents, if you look at the graph there, the red represents a typical consumer component for a mission profile. So this is a typical bathtub curve where you see the input mortality, and then you see the thing flattening out, and then you see an accelerated failure. So the flattening is normal operation, and then on the right-hand side is when thing starts to fail again. Below it is the expectation of automotive. So this is an expectation of an automotive mission profile. And you can see that, simplistically, looking at the PPM, the rigor of automotive mission profiles is much higher. Another way to look at the mission profile is to look at the duration in a number of hours as a percentage of the temperature, and there's a table defining that. Okay? So we have new methods in order to support the mission profile for ESD and latch up. I talked a little bit about ESD. I basically said that the packages for ADAS chips are getting very big, so you're moving from a CDM of, say, 6 amps to 9 amps. Latch up I didn't mention so much, but the interesting thing about latch up here is that with the more advanced nodes, you have a very low impedance substrate. That low impedance substrate starts basically causing interference between devices, making your device latch up. Okay? The electromigration requirements for automotive, remember I talked about those metal lines? They also need to meet that 1 ppm level. Transistor aging is based on 1 ppm. We look at a plus or minus 5 sigma design variation, and that's represented by a CPK level of 1.67. What that basically means is that you've got to have a lot of silicon now as an SoC or IP developer in order to do testing to give you statistical relevance, okay? The H-toll is moving up to 1,000-hour testing. So you can see that product reliability for automotive really impacts the way you think about your design methodology, the way you do your design work. So as Sushil introduced my profile, my background, I like to talk about physics, and any excuse I get to talk about physics, I'll use it. So as you're looking at these slides, you don't have to understand the detail, it's just me showing off that I know something about physics, okay? So aging accelerates in automotive. I think you get the message, right? You've got elevated environmental conditions that make things age faster, right? I also made the point that different phenomena age at different rates. So you have this concept of asynchronous aging vectors, especially for logic libraries. I mentioned a concept called NBTI, so negative bias thermal instability. This really impacts your PMOS devices. So if you've got a 7-nanometer ADAS chip, you're concerned about NBTI. And this is because the transistors hold data for long periods. And one of the ways to explain NBTI is this graphic on the right-hand side. So this is a cross-section of a transistor. You've got the poly, the gate, and basically the substrate where you bias the device. And the H represents the hydrogen ions. So what happens is when you apply a bias to the gate, so 0 volts for a PMOS transistor, the hydrogen ions basically disappear, except one, and then he comes back, and they come back. So all's good. So the NBTI concept basically is dependent on time. If you stress the device long enough, those H's, those hydrogen ions, get stuck in the upper layer, and they never come back, causing a permanent shift in your threshold voltage. Okay? The hot carrier effects are related to the amount of switching. That's important to consider because these ADAS chips are switching very fast as they're processing real-time data. The oxide breakdown is basically related to the green section here on the poly. And then you have the electromigration where the currents or the electrons are flowing in the same direction. So we know these things, right? We talk about them. So what do you do in terms of design to solve the problem? You can't go back to the foundry, especially at Synopsys. We can't go back to the foundry and tell them, hey, your process isn't working. You've got to basically figure out a way to mitigate against that. So this example shows the mitigation of the NBTI problem of a differential input stage on any kind of block that you see in an ADAS chip, be it PCI Express, LPDDR4, PCI Express, or MIPI or HDMI. So what we're doing here is we're basically introducing an asymmetric stress on both, a symmetric stress on both inputs of the differential pair and getting around the aging problem by a circuit technique. Okay. What we've seen in the second and third generation of FinFET technology, the concepts like PBTI on the NMOS device can be ignored. You don't need to worry about them. The hot carrier injection or the hot carrier effects do get worse with higher fields. And here, to solve that problem, is that you can lower the VDD, okay? which is a very nice way of getting around the HCI problem. The time-dependent dielectric breakdown, so this is related to the gate oxide, especially when you get to the narrow technologies. These are very statistical in nature. There's no unified model. You've got consequences in the dielectric. It's very low. You have situations related to the metal pitch, the higher capacitance, the higher electric field, the lower permittivity. The oxide is weaker. It's more porous. So you really have to figure out a technique to make sure that you protect the biasing of your devices so you don't get into this aging effect related to the gate oxide and the device failing. So I just gave you a whole bunch of physics, right? What it boils down to is your mission profile. Okay? So understanding all that physics and all the fun stuff with the electrons and things failing and getting older, that understanding applies to the way you think about your design, and it applies to the way that you make your design robust and reliable to a mission profile. So another interesting anecdote. So when we started in this market, in this automotive market, people were talking about grade 2, grade 1, 125, 150, and heads were spinning, and everything needed to work forever on 150 degrees C, and all our stuff was designed to 85 degrees C, and it's kind of very confusing. And after a while, we started understanding a little bit better that there was this concept called a mission profile where the temperature was related over time, simplistically. So I was like, oh, great. I'll go to one of the automotive OEMs and ask them for their mission profile, and if I have that mission profile, I can design our IP to that particular profile. And what I didn't realize was that these mission profiles are secret. Okay? The OEMs, the automotive companies, the SoC companies do not share their mission profile because their value add is to design SoCs and IP that is robust against that particular mission profile. Right? So they don't want to share what that profile is. And so when I was preparing for this presentation, I actually put Synopsys' mission profile on the slide. And somebody said, hey, you can't show that, it's secret. So this is not the Synopsys mission profile. It's an example of one. If you're interested, we're happy to discuss with you what that profile looks like. But there was a lot of work gone into generating that mission profile. So essentially, what you're doing here is you're expressing the number of hours spent at different temperatures. Okay, so all the heavy stuff is over. What I'm going to show you now is a bunch of IP that we've developed to support automotive grade. And as I'm going through that, I'm going to give you some design information about how we got there, okay? So now we have a big set of IP blocks that support basically almost all functions that are needed for infotainment, for ADAS, and even potentially MCU. We categorize them as interface IP, processors, subsystems, security, analog blocks, and some foundation IP. So I'm going to talk about high-speed memory interfaces now. This is real. We have customers now building ADAS chips, going to 7 nanometer, asking for LPDDR4 at 4267 megabits per second. Okay? So you can see the way we've implemented the design with the D bytes, the ACX4s, and certain digital control that we include in the BIST. Remember, this is an automotive IP, so this is ISO 26262 compliant. It's going to support ASIL B. Through a customer discussion, we can also get this to ASIL D. And remember all the things you've got to do in order to meet ASIL D. We've added all the quality documentation. It's certified, meaning we've got the digital IP that does the memory controller and the PHY that talks to the DRAM that works together as a certified solution for automotive. And we have all the characterization reports to show that we're meeting AEC Q100. From a digital IP perspective for memory controllers, the safety features include inline ECC. They include address command protection within that ECC. They include on-chip parity. In data path, they include configuration registers to do error detection. So you can see a lot of work was done on the digital IP, a lot of work was done on the physical IP in order to make a complete LPDDR4 solution to go up to 4267 megabits per second. The quality documentation includes the DFMEA reports with a quality analysis and rankings. This is the PCI Express Controller, again, including a bunch of automotive safety features. Okay? So at the top, you see this concept called RAS, reliability, accessibility, and serviceability. For debug, error injection, and statistics, we've also added parity protection for the internal data paths. And that actually goes through from the AMBER interface, through the AMBER bridge, right down into the individual blocks of the PCI Express controller up to the pipe interface. And then on the periphery, you see what we've done to that digital IP to support the automotive safety features to meet ISO 26262, parity protection, receive data error flags, advanced error reporting, ECC, system fabric stuff, data path protection, watchdogs, and configuration registers. So that's what we did for PCI Express controllers in order to meet automotive safety requirements. So significant changes to your RTR. Ethernet. Remember at the beginning, I showed you a slide from BMW. They're projecting Ethernet to be a very important connectivity for use in cars. This is the Ethernet controller that we have in my group. And here, it's supporting ADAS. It supports a concept for AVB, audio video bridging. It also supports TSN, time-sensitive networking. It's optimized for a lot of the automotive multimedia requirements. It has safety-critical features. And it's been tested with UNH. The development board has been created especially for customers that want to develop software for their automotive applications. So they don't need to wait for the SoC. They don't need to wait for the IP. They can get this development board. It's an automotive development kit, and it helps our automotive customers develop their automotive software months and months ahead of time before they get the hardware. Right at the beginning, I touched about security, and, sorry, excuse me. Right at the beginning, I touched about our processor technology ARC, and also a little bit about security. I'm combining the two here. So in order to meet ASIL D, I mentioned that it's the highest ranking in terms of a safety level. You add a lot of redundancy. For the ARC example that I'm giving here, what you're implementing is a shadow core that's managed through a safety monitor. And the safety monitor is lockstep with the main core. And this has hardware safety features included. So in order to meet this very high requirement, you basically add a lot of redundancy and a safety monitor. For security, what's interesting is that hackers for automotive, for example, are becoming very sophisticated. So some of these individuals or groups can sense the temperature changes on the ADAS pin. So you've got a big ADAS chip, you've got lots of pins on the side, then can actually figure out functionally what's going on by looking at the temperature changes on the pin. And they're able to figure out, the traffic profile from that. And that's called a side channel attack, right? And so if you've got a trusted execution environment or a hardware root of trust, you can actually secure your ADAS chip and your processor using this technology that I'm showing here in the middle. So you secure side channel attacks against that. And then if you want to go full-blown with your security requirements, we have the trusted execution environment that includes a lot of cryptography blocks and cryptography cores, hardware accelerators, and security protocol accelerators to support that. That whole thing is called a trusted execution environment. And the point is that the more security you add to your ADAS chip, the slower things become. And so the way to get around that is to use security protocol accelerators. Okay, so to close out, I gave you a lot of information to get to automotive compliance. So to bring it all together, there's a lot under the hood. Hopefully I gave you some kind of perspective of the type of work that we've done at Synopsys in order to meet that. What we've done is come up with a concept called an Automotive IP Package. Okay? So you've got your standard IP, you've got your automotive IP. That automotive IP is managed through an automotive package in terms of deliverables, right? So we've met the 150 temperature requirements, 150-degree temperature requirements. We've added all the documentation that's needed for auditing. That includes the safety package, it includes the reliability reports, and it includes the quality reports designated by DFMEDA and QA manuals. This, amazingly, is now being supported at the advanced foundry nodes. So that's kind of really impressive how fast this industry has moved in terms of the technology nodes that are going into the advanced ADAS chips. So that's the end of my presentation. I just wanted to, before we open up for questions, acknowledge the team that helped in putting this presentation together. So all these individuals at Synopsys, BMW and Infineon helped in making sure that I presented good information. So thank the team for that. And also I gave a bunch of acronyms. I may have even got some of them right. So this is the aide memoire if you're interested in the acronyms. And certainly if you want to get into the automotive space, you need to memorize the acronyms on the right-hand side because they're the ones that come up very frequently nowadays. So thank you very much.